specs was to build a sphere instrument that also measured like a 45-0 instrument. And so the correlation to 45-0 is fairly good on high gloss surfaces, but as the gloss diminishes, so does the correlation to that 45-0 instrument. So at lower gloss levels, 45-0 and specs instruments don't match so well, but at very high gloss levels they do. And this is because the gloss trap can't capture all of the diffused light from the specular reflection when you're dealing with lower gloss materials. So here we have measured this black panel, both sides of this black panel with each of these three instrument geometries. And so the 45C0 instrument, C just stands for circumferential illumination, so this is still a 45-0 instrument. And when we measure both sides, we're now seeing significant differences in the L value between the glossy side and the non-glossy side. And that matches up with what we see visually. So we say that 45-0 instruments measure color as we see it. We see the glossier side being darker, and the 45-0 instrument measures a much lower L value for the glossy side. Now this is a neutral black color, so there's not much chroma to it to begin with, and so we're not seeing very much difference between the A and the B values. Now the D8 specs geometry, that is going to measure similar to the 45-0, and it is also going to see significant differences in the L value between the glossy and the non-glossy side. However, the spin geometry, the sphere spin instrument, which ignores the gloss and only measures the pigmentation, is going to measure these two sides as being essentially the same. It's not going to see the large L value difference that we're seeing because it ignores the effect of that surface gloss, and it only measures the pigmentation, which for the two sides of this sample are more or less the same. Now we have our measurements of that red panel of the glossy side versus the non-glossy side. And with our 45-0 instrument, we're still seeing some differences in the L value. The glossier side is still measuring at a lower L value than the non-glossy side. But now, because this is a very chromatic color, we're also seeing differences in the A and B values. So we're going to measure, the 45-0 will measure the glossier side as having higher A and B values as being more chromatic than the non-glossy side. And again, that matches up with what we see visually. Similarly with the specs instrument, again, it is going to see somewhat lower L values on the glossy side versus the non-glossy side. And also it is going to measure the A and B values as being higher on the glossy side versus the non-glossy side. But then again, we look at the D8 spin geometry, and we're seeing that it is measuring both sides as being essentially the same. And again, that is what we expect because we know that the pigmentation of these two sides is the same, and that spin geometry is going to ignore the surface gloss, the surface structure, and only measure the pigmentation, and it is going to measure them as being essentially the same. So our Spectra 2 guide instrument measures color and gloss in one. So it's a single instrument that can measure both because we know that both are essential to get the overall look of the surface. And so this instrument comes in both D8 geometries, where it does spin and specs in one instrument. So one single D8 instrument that does both modes. And it also comes in a 45C0 model. Now the illuminated measurement area is 12/8 millimeters, and that just means that the actual opening, the aperture of the instrument is 12 millimeters, but the actual spot size that it is measuring is 8 millimeters. And this also comes with the built-in 60-degree gloss measurement with an illuminated measurement area of 10/5 millimeters. And this is a true gloss meter, and you can expect the same excellent technical performance from this built-in gloss meter as you would from our standalone micro gloss meters. So here's a look at the inside of the 45-0 Spectra 2 guide, and it uses 6 white LEDs arranged in a circle to provide that circumferential illumination. And it also has that built-in 60-degree gloss light source and detector, which measures according to international standards such as ASTM, ISO, and others. And here we get a look at the inside of the D8 geometry Spectra 2 guide. And so this uses diffuse illumination with one single white LED, which comes in from the side. That light source, again, bounces all around the inside of that integrating sphere. We have two detectors, one for the spin measurement, one for the specs measurement, and also a light trap, which opens up to measure in specs mode. So this is one instrument that measures in both spin and specs mode. And again, this has the same 60-degree built-in gloss geometry that the 45-0 instrument has, which is also according to these international standards. So the Spectra 2 guide, we call it the revolution in portable color control because not only does it measure color and gloss, but it has a built-in fluorimeter. This is the first portable fluorimeter on the market, and this allows for color stability prediction. It detects fluorescent light excited in the UV and the visible range. So this goes back to light fastness, which I mentioned in the beginning, which is how stable the color is going to be over time. So it allows for quantification of fluorescent light with a fluorescent slider, and it also allows for calculation of color data after fluorescence decay. So let's begin with what is fluorescence. So fluorescence is when a light particle, a photon of a particular wavelength, a particular energy, strikes a molecule, particularly an electron in that molecule. And if that photon is of the right energy, that electron can absorb that photon, and then it will jump from a ground state to an excited state because it now has more energy. But electrons don't really like being in excited states. It wants to go back to its ground state, so it's very quickly going to give that energy back off in the form of heat and light. But because of conservation of energy, the amount of energy it absorbs is going to be equal to the amount of energy it gives back off. And since some of that energy goes towards heat, the photon, the light particles that it re-emits, is going to be lower energy than the one it absorbed. And for light, lower energy equals longer wavelength. So it's absorbing light of a given wavelength and re-emitting it at a longer wavelength. And this is what we refer to as Stokes shift. And so the fluorescent light, the re-emitted light, is always going to have lower energy and longer wavelength than the excited light. And so a fluorescent material can absorb light in the UV range and emit it as blue light. It can absorb blue light and re-emit it as green light, green to yellow, yellow to red, but it never goes longer to shorter. So you can never, for example, absorb yellow light and re-emit it as green or blue light. So we have our two geometries of the Spectra 2 guide instrument. And the fluorescent measurement comes from monochromatic illumination to excite the fluorescent material. And this comes in the form of 12 LEDs ranging from 360 to 660 nanometers, 2 LEDs in the UV range, and 10 in the visible light range. And we built in a fluorescent slider into our Smart Chart software to show the excitation and emission range of the fluorescent material. So now I will demonstrate that to you. I'm going to switch to my Smart Chart software. I have some readings saved in here. And so I will go to my fluorescent slider. And so we have a measurement of our standard and we have a measurement of our sample. And up here in this slider are these are 12 numbers corresponding with the wavelengths of those 12 LEDs that are used for fluorescence detection. And I can take this slider and I can move it along to see where the fluorescent emission is. So you can see in the graph, it's not telling us how much reflection there is at the same wavelength. It's only telling us how much re-emission there is at longer wavelengths. So this is only showing us the fluorescently shifted light, not just the reflected light. So as I move this slider along these different LEDs, I can see where most of this fluorescent light is coming from. So I can see that for the standard, the fluorescent emission seems to peak with the 570 nanometer LED. So for the standard, it seems like I'm getting peak fluorescence where it's absorbing 570 nanometer light and re-emitting at longer wavelengths. For the sample, if we look at the bottom graph, it looks a bit different. So it looks like the peak wavelength here is at about 520 nanometers. It's absorbing 520 nanometer light and re-emitting at longer wavelengths. So there are some differences between the sample and the standard. And if I look at the slider, it looks like overall there is more emission, more fluorescence altogether in the standard than there is in the sample. Back to our presentation. So the Spectra 2 guide, in addition to giving you that fluorescence slider, it also calculates new indices, delta E FL or delta E fluorescence, and also delta E 0. So delta E fluorescence indicates whether and how much fluorescent energy is emitted. And it is calculated by taking the original specimen and comparing it to the specimen after estimated fluorescence degradation. So what it's doing is it's measuring the sample as it is now with fluorescence and calculating the color values based on that. Then it takes the fluorescently emitted light and strips that away and calculates what the color would look like without fluorescence. And it takes the color difference between the two. So the delta E fluorescence is simply the overall color difference between the standard as it is now and the standard as it will be once all the fluorescence has decayed. Same for the sample. It calculates the delta fluorescence for the sample as well, which is what it looks like now versus what it looks like after fluorescence has decayed. And then it also calculates the delta E0 value, which is a calculation of the estimated color difference after fluorescence has decayed. So this is the difference between sample and standard after all fluorescence is gone from both. So just as another maybe easier way to look at this, you have the standard, you measure the color of your standard, you measure the color of your sample, and calculate the color difference between the two. That's the delta E value. The Spectra 2 guide then calculates what the standard will look like after all the fluorescence has decayed, and it calculates the color difference between the standard now and the standard once after fluorescence decay, and that's delta EFL. Same for the sample. And then it calculates the color difference between standard and sample after the fluorescence is gone from both, and that is the delta E0 color difference. So I'd like to go back to Smart Chart, and now we can take a look at these color values. So up here, these are the values for the standard, and down here, these are the values for the sample. So we can see with the sample, the delta E fluorescence value is 0.39. So we know that after all the fluorescence has decayed, the color will have a color difference of at least 0.39 versus what it looks like now. If we look at the standard, the delta fluorescence value is 1.02. So it's going to be a slightly larger difference for the standard between what it looks like now and what it will look like after fluorescence decay than the standard. Than the sample. And so this sort of backs up what I said before when looking at the fluorescence slider, where it seems like the standard has more fluorescence than the sample, and we can also see that from the delta E fluorescence value as well. And then we have the delta E 0 value, which tells us what the difference between the sample and standard will be, again, after fluorescence decay. And we can see that the lack of fluorescence, the color change caused by that fluorescence going away, is going to be 2.01. So here I have two test series. What we're looking at now is the original sample and standard before weathering, but then these two panels were put through some weathering tests. We have that data here. So we can see that the delta E fluorescence values are now 0 for both standard and sample. So these have been weathered to the point where all that fluorescence has decayed, all those fluorescent pigments have broken down, there's no more fluorescence. And we can see that backed up here in the fluorescence slider. There's no more fluorescent emission showing up in this slider. And we can see now that the delta E value between sample and standard is 3.15. This is the actual color difference after weathering. If we look back here at the original sample and standard, the original color difference was 0.67. And our predicted delta E 0 value was 2.01. And we see that the actual difference after weathering is 3.15, so a bit higher. But of course, fluorescence degradation is not the only source of color change. It could have to do with things like gloss change or just a general breaking down of the absorption pigment in the material. Back to our presentation. So in addition to being able to look at this data in the software, the Spectra 2 guide has a visual and acoustic signal to indicate fluorescence during measurement. So there's a blue status LED which lights up to indicate that fluorescence is detected. And this only lights up when the emitted energy is greater than 1% of the excited energy for any one of the 12 LEDs used for fluorescence detection. So it's a very tiny, negligible amount of fluorescence. It will ignore that. But if it is a significant amount, at least 1% of the excited energy, it will light up blue to indicate that there is fluorescence in the sample. It also has a pink status LED, which lights up to indicate that the amount of fluorescence has exceeded the defined limit. So this means that the difference between the fluorescent and non-fluorescent sample, or the fluorescence before and after decay, is larger than 1/3 of the tolerance. And this tolerance can be customized in the software. So pink LED essentially means that there's too much fluorescence and it is out of tolerance. So when setting up a global color management system, the common practice is that you have a master standard. This is your target color that you want all of your products to look like. And from that color, a number of certified working standards would be produced and then distributed to any plants or suppliers making products in that color. So every plant uses their own certified working standard for instrumental control. But this introduces several sources of error. One is that working standards can differ from each other. So as much as you might try to make all of those standards match each other exactly, we know that that's not always exactly the case. It's impossible to make them match exactly. So there is going to be some slight differences between those certified color standards. There could be error due to operator influence and also inter-instrument variation. So this leads to practical consequences requiring the discussion of, is this measured color difference a real color difference, or is it just due to one of these sources of error? So in this case, visual color approval becomes more significant, which can be very subjective. So this is not ideal. So the ideal way to do things is to use digital standards, which provides for one binding reference used by all locations worldwide. So plants and suppliers are using the same master panel, and they're all using a digital master standard that all has the same color data in it for instrumental control. And to do that, that requires an instrument with excellent inter-instrument agreement, such as the Spectra 2 guide. And so here we have taken several different Spectra 2 guide instruments of the same type and measured several different samples with them. And here we're showing you the color stability, the excellent inter-instrument agreement between these instruments. Here we have several neutral colors from pale gray to mid-gray to dark gray. And we can see from the L, A, and B values that they all are measuring to within a 0.1 unit or less of each other. Similarly, with these chromatic samples, we have a red, a green, and a blue, these very chromatic samples. And again, the inter-instrument agreement between these instruments is very, very tight, and you're going to get the same color values to within 0.1 with all of them. Part of the reason that we can do this is because we use LED technology. We have smart testing of these LEDs combined with long-standing experience. We've been making LED instruments for more than 2 decades, and this guarantees outstanding performance. We do provide a 10-year warranty on the LED light source because it is simply that stable. It never requires a lamp replacement, so it's very low maintenance. And it provides for very high repeatability, both in the short and long term. It provides homogeneous illumination and very good temperature stability from 10 to 40 degrees Celsius. For my American cohorts, that is 40 to 104 degrees Fahrenheit. And this allows for excellent inter-instrument agreement. And for digital standards. So digital standards bring the complete supply chain on target. It allows for one binding reference. It minimizes error sources. Electronic instrument standards take the place of certified master standards. The standard is being measured once in one location by one instrument and then distributed electronically to all the plants and suppliers that need it. And BYK provides the only instruments with the excellent accuracy required between instruments to allow for the usage of digital standards. The Spectra 2 guide also comes with our Smart Chart software. We have Smart Lab. Each of our instruments has a Smart Lab module specifically designed for it. So there's a Smart Lab module specifically designed for the Spectra 2 guide, which allows for online measurement and memory transfer, data analysis in all color systems with scatter and line graphs. So it provides an array of graphical representations. You can adjust the color systems, difference equations, illuminance, all sorts of things to look at your data any way you want. And as I showed you, it provides a color stability check with that fluorescent slider. We also have the Smart Process module, which is designed for production plants. This allows for standardized QC. It has a sampling process with digital standards defined in organizers. You can save your data in SDF databases, and it allows for comprehensive data analysis with easy filtering and statistical analysis. So back to Smart Chart. There is just so much stuff I could show you in Smart Chart, but the one thing I'm going to show you today is digital standards. So first, I'm going to measure a standard. I have my Spectra 2 guide D8 instrument connected to my computer. I can rename it up here. So this will be Corey's Awesome Color. And I'm going to go ahead and measure my color. And here I have my standard, Corey's Awesome Color, with my color values here. I measured something that is fluorescent, so I'm getting my delta E fluorescence value, and also my gloss value with that built-in gloss meter. Now what I can do if I want to is I can now right-click this and save this standard in my standard database. So now I'm going to switch over to standard management, where I see Corey's Awesome Color. And you can also create and measure standards directly in standard management as well. So I can now go here, and again, I can see my LAD values for my standard, and I can define this as a master standard, which means that it can now be used as a digital standard. So now I need to distribute this standard to any suppliers or sister plants that may need it. And so I can export this standard as a simple XML file. This can be emailed around to whoever needs it and then imported back into their smart chart software. And I can then go into instrument management, and I see my Corey's Awesome Color standard, and I can take that, it is currently in the database, and I can just click the arrow to send it over to my instrument, and then I can now go down to the floor, the production line, and take some measurements using my new standard. So it's as simple as that to use digital standards. Back to our presentation. So now the Spectra 2 guide, not only does it do color and 60-degree gloss, but it also has that built-in fluorimeter for fluorescence quantification built right into the portable instrument. So it has a balanced and upfront design with a large color touchscreen. One of my favorite new features is the live preview of the measurement spot. And so it has a camera built into it that looks directly down through the aperture so that when you're positioning the instrument for measurement, you can activate that camera and you can see exactly the measurement spot that you're going to be measuring. So you can use it to avoid any scratches or imperfections in the panel, so you can get a perfect color measurement on a perfect spot. It can also be used if you're dealing with very small samples that might not be much bigger than the aperture itself. This is great for positioning those small samples directly underneath the aperture. As mentioned, it has smart high-tech LEDs with peak performance that allows for digital standards. And it comes with our smart chart software that allows for data analysis using either a Wi-Fi or a USB connection. So this does allow you to communicate via Wi-Fi, so you can go completely wireless if desired. So here's our lineup of Spectro instruments, beginning with the basic instrument, the Spectro Guide. Now this instrument still has excellent reproducibility, which of course is another term for inter-instrument agreement of about 0.2. So you can expect any two models of our Spectra, or any two Spectra guides of the same model to agree with each other to within a 0.2 delta E. This also comes with a built-in 60-degree gloss meter, and it includes our EasyLink software, which is a simple spreadsheet program for downloading data, and it has some fairly useful data analysis functions in there as well. Next up, we have our new Spectro 2 Go instrument, and this has that improved reproducibility or inter-instrument agreement of 0.1 delta E, which allows for digital standards. This also has the 60-degree built-in gloss meter, and this instrument includes our Smart Chart software. So you get two licenses for either Smart Lab or Smart Process included in the price of the instrument. Next up, we have the Spectro 2 Guide instrument, which is currently available. This also has that excellent reproducibility at 0.1 delta E. It has the built-in 60-degree gloss measurement. But this instrument also does that fluorescence measurement, so for quantification and measurement of color stability. And this instrument also includes the Smart Chart software. And then we have our top performer, our new Spectra 2 Guide Pro. This has even better reproducibility, allowing for digital standards. It also has the 60-degree built-in gloss meter. It does the fluorescence detection, but this meter is really specialized for jetness measurement. Now, if you don't know, jetness is a measure of how black is your black or how deep is your black. And so when dealing with jetness measurements, by the nature of such measurements, you're dealing with very, very dark colors which have very, very low reflectance. And so when you're dealing with such a small signal measured by the instrument, the noise to signal ratio is amplified. And so when you're dealing with very dark colors, in order to measure jetness in an accurate and repeatable way, you really need an instrument that is very precise and very repeatable, even at that low reflectance range. And that's what the Spectra 2 Guide Pro specializes in. And of course, this instrument also includes our Smart Chart software. So the Spectra Guide and the Spectra 2 Guide are currently available. The Spectra 2 Go and the Spectra 2 Guide Pro will be available soon. I believe currently they should be available sometime in October. And here you are looking at, despite what you may think, these are not movie stars, nor are they supermodels. This is actually BYK Gardner's technical service team, both my colleagues over at our headquarters in Germany, as well as those of us here in the US. And we have our contact information listed, both our emails and our phone numbers, because we would love to talk with you. You don't have to wait for a webinar to get your questions answered. We can talk with you anytime. Shoot us an email, give us a call. We'd love to discuss your application with you. And just some cleanup announcements. So our next webinar will be on film thickness and adhesion of coatings on the 15th and 16th of July. See our website to sign up for that. We also do on-site seminars. Of course, times being what they are, we have not been doing any of these recently. But once there's no longer a killer virus on the loose, we would love to pay you a visit. We can design a seminar specialized for your needs and your applications, and we can bring our instruments, and you can touch them and measure with them and see what they actually look and feel like to measure with. We have a new website, BYK-instruments.com. Check it out. And we also have a number of instructional videos on YouTube. You can check them out at youtube.com/user/BYK video. Or I would bet that if you go to YouTube and just type in BYK, that you could reach our videos that way. And of course, if you'd like to pay us a visit, we'd love to have you. So at the top left there, we have our US headquarters here in Columbia, Maryland. We'd love to have you and show you around. Of course, we're very close to Washington, D.C., so a lot to see around here. At our bottom left, we have our worldwide headquarters in Geretsried, Germany. That is our primary production facility. So my colleagues in Germany would similarly love to have you. They'd love to host you there and show you around our production facility and all the wonders of Germany. As you can see at the bottom right, if you didn't notice, Germany actually makes and sells beer. Myself, being the scientifically minded person that I am, I have done thorough and exhaustive analyses of this beer, and I have concluded that it is in fact excellent, among the best in the world, second perhaps only to that made right here in the US. And with that, that concludes my presentation, and we will move on to the Q&A portion. Okay, so one question I get quite often is about the gloss meter that's built into our instruments, the Spectre Guide and the Spectre 2 instruments. Now this is a true gloss meter. It is an actual built-in gloss meter with its own light source and detector. This is in opposition to some of our competitors which claim to have built-in gloss, but what they're actually doing is using a calculated gloss value. And so what that is it's a D8 instrument that does spin and specs, and when you're taking spin versus specs measurement, the difference between the two measurements is that you are removing the specular reflection from the specs measurement. And so theoretically, if you take the spin measurement, the amount of reflectance you get in the spin measurement, and subtract the amount of reflection you get in the specs measurement, the difference should be something like a gloss value. But this method of measuring or calculating gloss is not very accurate. It doesn't really match up very well with certified standards. And so in order to get true accurate gloss measurement, you really need an actual built-in gloss meter that has its own light source and its own detector. And that is what we include in all of our Spectre Guide instruments. So we have a question asking, is that only 60 or as well 20 and 85? So the Spectre Guide instruments only have the built-in 60-degree geometry. This is the most commonly used geometry worldwide. And the reasoning for that it only has that one is just it has to do with the angles involved in the 3 different geometries. It's really only practical to build one into the instrument, so it does not do the 20 and the 85. If you have a need for very low gloss or very high gloss measurements, of course 20 20 degrees is meant for high gloss surfaces, 85 degrees is meant for very low gloss surfaces. If you have a need for that, you should buy one of our standalone micro gloss instruments. So I got the question, is the new instrument capable to detect color stability also for metallic and mica paints? To a certain point, it could certainly detect if there is any fluorescence in those paints. The problem is with metallic pigments and mica, what you really need is a multi-angle color instrument such as our BYK to fully quantify color in those materials. And the reason is because when you deal with pigments like that, the color, the lightness and darkness in particular can change drastically depending on the observation angle. So it's not enough to just measure at one angle, such as with the D8 or the 45-0 instrument. You really need a multi-angle color instrument. So one question is why sphere or 45-0 might be better for different applications. So one reason 45-0 is generally better for color harmony. If you're dealing with materials like appliances that might have different panels or different parts that are sometimes manufactured at different facilities or even by different companies, when those parts come together, they all need to look good. And so what you might end up having is slight gloss differences between these different parts that are supposed to look the same. And of course, we know that gloss differences can cause the color to look different. So it's not enough for color harmony just to look at the pigmentation, because differences in gloss could still cause different parts of an appliance to look different even when the pigmentation is the same. So 45-0 is generally preferred for color harmony. because it really is color as we see it. And so if there are slight gloss differences, that can be mitigated by adjusting the color slightly. So you really want to measure what we see for products like that, and not just the color pigmentation. Now on the other side, sphere instruments are generally preferred. Sphere spin instruments are generally preferred for weathering studies. Weathering, of course, is where you take a product and you either put it through an accelerated weathering machine, or you just sit it outside for a period of time just to see how well it stands up to the elements and what the actual color stability is. And the reason sphere is preferred for that is because when you measure your color before weathering and you measure it after weathering, if you're measuring with a 45-0 instrument and it detects color change, you don't really know whether or how much of that color change is due to an actual change in pigmentation versus change in the gloss. So with sphere instruments, you can isolate changes in pigmentation versus changes in gloss with the built-in gloss meter. And so that's why sphere spin instruments are generally preferred for weathering studies. So that seems to be it for the questions. If I wasn't able to get to your question, you can email me and I can answer that offline. I want to thank everybody for coming today and hope you all have a good rest of your day.